Hi, welcome to the Signal Path. In the past 14 years or so, we've done so many videos about electronics and microwave and a variety of electrical systems. I think it's time to completely rebrand ourselves, throw everything away, and start from scratch. Hi, welcome to the Chemical Path. In this episode, we're going to make liquid oxygen from scratch. Now, why liquid oxygen? Well, I'm glad you asked. And now that we established that, based on my research, if I want to make liquid oxygen from scratch, I need to make oxygen from scratch. And for that, I need nucleosynthesis. So helium and helium can make beryllium, and then beryllium and helium can make carbon, and then carbon and helium can make oxygen. And for that, all I need is a star with 8 solar masses just before it goes supernova. Okay, we're going to make liquid oxygen from oxygen. So we need a way of extracting oxygen through some known processes. Now what I want to do is I want to put electricity into this system on one end and get liquid oxygen on the other end. So there's a lot of really interesting physics and chemistry that needs to happen in between for this end-to-end process to actually work. So let's get started. Well, if we want to have electricity do the work for us, we can simply use electrolysis, use electric current to break water down into its primary elements of hydrogen and oxygen. Here I have a solution of water and potassium hydroxide, which is acting as an electrolyte, and I have 2 copper plates inside of it. I'm going to apply 10 volts to it, and at 10 volts it's going to draw about 6 or 7 watts. And look at that, on the left side, we're getting hydrogen, and on the right side, we're getting oxygen. And there's going to be a lot more hydrogen, twice as much, of course, because there is 2 hydrogen atoms in the molecule versus 1. Now, this is all fine, but it has several key disadvantages. First of all, we need to constantly replenish the water. I didn't want to have something that I need to replenish. I only wanted to use electricity. But the second problem, which is much bigger, is that aside from being able to having to separate the oxygen and hydrogen from each other, which is not too difficult, the oxygen coming from the positive terminal is going to have a lot of water vapor in it. And we're going to have to remove that water vapor as much as possible because we don't want that to get into the chamber. It's going to freeze and it's going to cause all kinds of problems. So drawing this out would be a challenge. Needless to say, there are a lot of chemical ways to accomplish this also. For example, you can use hydrogen peroxide and use a catalyst like manganese oxide to extract the oxygen from that solution. But that suffers from similar problems. It's going to consume hydrogen peroxide constantly, of course, and it's going to have a lot of water vapor in the oxygen mix again. So I want to move away completely from these techniques. I want to use a kind of a physical, mechanical mechanism to do this. Let's see how that's done. So if we truly want to only add electricity to our system and get oxygen out without invoking any chemical reaction, a really good way to do that would be to use the PSA, which is a pressure swing absorption technique. In this technique, you extract the oxygen straight from the air because we have 21% of it in our air composition. So if we can remove most of the nitrogen from it, we will be left with purely pure oxygen. And that technique is now really common and can be scaled to really large devices. In fact, these things have become so much cheaper since the pandemic because of obvious needs for additional oxygen, both from home use as well as hospitals. And you can store the oxygen that comes out of this. Now, one thing to keep in mind is that this is not going to give you laboratory grade oxygen where the purity is 99.99% because of the limitations of the system. But it's going to reach over 90% fairly easily, and that's pretty nice for what we want to do. Now, at the heart of a system like this, there is some zeolite, which is going to act like a molecular sieve, and it's going to absorb nitrogen preferentially over oxygen. Now, this is not entirely because of the size difference between the nitrogen and oxygen molecules. In fact, the kinetic diameter of a molecule of oxygen is 3.46 angstrom, but it's only 3.64 for nitrogen. So their size differences is not that much. In fact, the majority of the absorption is due to the electrostatic effects within the crystalline structure of zeolite, which is going to prefer to absorb nitrogen. Although the size, of course, does play a role in there as well. Now, in order for the molecular sieve to work, you need to put some pressure behind it, and we'll talk about that in a second. So air is going to come in from the outside and it's going to go through some air filter. Now this is super critical. In fact, there are multiple air filters in a system like this cascaded, even though here is only showing one. And you can imagine why. Because these zeolite molecular sieves already have very, very fine porous structures. If you add any dust or any additional particles enter the system, you're going to clog the zeolite, and then there's no way to clean it out. You're going to have to throw it away. So filtering the air before the next step is really important. Afterwards, you're going to have a compressor. Similarly, this compressor should have no oil that comes out, no oil particles. It also has to be filtered. But because you're compressing the air temperature is going to go up as you compress it, and you don't want to pass hot air through this, especially if there is a patient on the other side who is going to breathe this afterwards, and you also don't want to heat up the zeolite. So there's some heat exchanger to make sure the air passing through the next stage is at least back to room temperature. There's some pressure regulator here to control what's going on. And then we have 2 tanks of zeolite, which is going to become clear exactly why that is. First, this path is open, allowing the high pressure air to enter this zeolite structure, and this valve here is closed. As you force the air with pressure through the zeolite, it's going to absorb a lot of the nitrogen, and the oxygen is going to come out the other side. In this case, it's going to go over here, and it's going to go out in our product tank. So here we're going to have high purity oxygen beginning to be stored. Now at some point, this zeolite structure, depending on the size of this particular can over here, is going to get saturated with nitrogen, and it will not be able to absorb anymore. Essentially, it's going to get clogged, but this time with nitrous gas. So as a result of that, we need to somehow replenish it and empty it. At this point, the system is going to switch, and it's going to change the valve, allowing the air to go through the other tank B in this case, and then it's going to open this valve. Now there's high pressure in here because it was pressurized just a moment ago, and then this tank now is over here is closed, allowing the nitrogen to exhaust back out. And the cycle is going to go back and forth, and it's going to repeat doing that. This allows the tank A to be discharged while tank B is purifying oxygen again. And this process can, of course, go indefinitely. And there's going to be some control units required to close and open these valves. But really, the process is pretty straightforward. Just like any sieve, once it's saturated with the stuff you don't want, you're going to have to dump it out, which is exactly what's going on. On the other side, this tank is going to get more and more oxygen in it. You can have a pressure regulated, so the oxygen that comes out of this side has a certain flow and a certain purity. Now you can also imagine that depending on the size of these cans, there's a certain rate of oxygen flow which you can support. If you have a big compressor with a lot of air coming in and a lot of surface area of the zeolite in big tanks, you can put a lot of oxygen out and switch back and forth between them. It's also not entirely inconceivable to imagine having more than 2 of these tanks and then just cycle between them for even faster regeneration of the nitrogen-oxygen composition. Now, at the same time, the nitrogen that's coming out here could potentially also be used, but for the majority of these medical devices, they don't care about that. They can just put that nitrogen back into the environment again because it's already mostly nitrogen anyway. And the oxygen purity in here can, as I said, reach 90-95%. So I have one of these, a fairly inexpensive one that I bought. So let's go and take a look at it and see how well it actually works and take it apart, see if we can identify all of these components. And here is our oxygen concentrator running. You can probably hear it. Now the controls of a unit like this are really simple because they're meant to be used by any average user. You have the flow in liters per minute, the number of hours this thing has been running, and the O2 concentration. Although I have huge doubts about this number, we'll talk about it when we actually take a look inside of it. Now I can adjust this. For example, I can say 2 liters per minute, and the oxygen concentration will drop. And that's because it has a certain amount of oxygen it can take from the air. So if you increase the flow, the concentration has to go down. And this goes all the way to 8 or 7 liters per minute. Anyway, let's leave it at 1, which is the highest level of concentration. You can see this comes back up, but again, I think this is fake. In the front is where the oxygen comes out, this little nozzle over here, and you can actually fill this little container in here. You can open this. You can fill this container with water, and that will add some humidity to the oxygen that you're breathing so it doesn't dry out your nostrils. But of course, we don't want that. In fact, we want the exact opposite of this. So we'll have to add further drying to this. But let's take a look inside of this unit. And here is what is inside of our oxygen concentrator. If we look carefully, we should be able to identify all of the components in here and relate them back to the block diagram that we were looking at before. In the middle of all of this is another container where the compressor is. It's basically the compressor housing. And there's a fan here on top of it. And that is to cool the compressor as well as the air as it gets compressed so that it's passed to the rest of the system roughly close to room temperature. It's also really important to isolate the noise of that compressor. And there's additional padding all over this device to achieve that because this could be sitting next to someone's bed, for example. Now in the back of the unit, right underneath over here, there's a very, very dense filter, which I will show you in a second. That is the air intake. That's supposed to block as much of the dust and particles coming from the outside so that the air intake goes through yet another filter, removing even more particles from this, and then it goes into the intake of the compressor itself, which is this pipe. On the other side, this is the compressed air coming out, and it goes into this valve over here. This is basically a motor connected to a valve which should constantly rotate, switching this compressed air from this hose into this hose back and forth, just like we explained before. And those are going to go into our zeolite containers over here, which are a molecular sieve. And the oxygen concentration is going to be achieved from the bottom over here, from this pipe. And this pipe comes over here and it goes in the front of the unit. There's another little valve over here which is controlled by this motor, and the only purpose of this is to mix in air depending on the flow that you want. So it's actually taking the air after it's been filtered, which is helpful because it's also compressed, so it has a pressure equalization built into it in a way. So if you want to increase the flow rate, it's just going to simply mix in more fresh air from the outside back into it until it gets the flow it wants to. Now note how there is no oxygen sensor in this at all, and I'll show you this PCB over here so we can take a closer look at it. There's actually a room for an oxygen sensor, but it's not populated, so that number in the front is definitely a lie. And this is the only interface to the front panel, which is some kind of an I2C or stereo interface to populate everything over here. And that's really it. There's not much else going on. We're going to run this and take a look at some of these things so you can see it moving around and take a closer look at the rest of the components. And here's the PCB. It's really quite simple. It has a few relays to control the various motors and the compressors, turning them on and off, and control the little valve there that mixes in additional air for controlling the flow. This is where the oxygen sensor would have gone, which is not populated, some DC-DC converters to run the microcontroller, and the serial interface to the front panel, which has the LCD and the settings and everything else. This thing over here is a high voltage power supply for air ionization. I don't know how effective it is, but it looks like it goes into the outtake or the intake of the actual pump over there. And here at the very bottom, this hose in here, this is the oxygen coming out from the bottom of the zeolite containers over there. Here's the other filter I was talking about. And here's the two motors. This is the valve that's going to go back and forth, and this is the controlling the flow there. And here it is running with an aid of a flashlight. You can see that rotation shaft, which is just simply passing the air from one valve into the other. Yeah, quite simple. And on the other side of the unit, we see a few other things. This is the main exhaust. This is where the nitrogen-rich gas comes out. So in theory, you could actually connect something in here and have some perhaps higher purity nitrogen coming from here as well. And this is the little capacitor for the compressor inside. The compressor is nothing really fancy. It's just a really basic compressor there. The fan runs for a little bit longer after the unit's been turned off in order to cool everything down further. And here's the main oxygen line coming out. Here you can see there are some beads inside of this. I believe these are noise suppressors so that the noise of the compressor doesn't travel through the tubes and comes out all the way into the user because you're going to be close to your ears. Yeah, that's about it. And here's the front end filter. I mean, look at how dense this thing is. You can't even tell it's really a filter. At first I thought it was a solid piece, but it has very, very fine pores. So you can imagine how good this will be at filtering things. And you can replace this after some time. So now I want to measure the actual oxygen concentration coming from our unit because I don't believe the number that's in the front panel. So I went ahead and I bought this oxygen analyzer. This is going to give us flow, pressure, as well as the concentration of the oxygen. Now in one of the previous videos, I took apart a gas analyzer intended for measuring the exhaust of various things during a burning process, and that also had an oxygen sensor in it, but that was an electrochemical sensor, and we took it apart and we did a whole bunch of analysis on it. I definitely suggest that you watch that video if you haven't seen it. But the principal operation of this oxygen sensor is actually different than the other one, so we should take this apart and learn how it works. And here's what's inside of our oxygen and pressure sensor. Now this instrument actually measures the oxygen concentration and flow from a different port that it measures pressure. And that's because it's using one of these digital independent pressure sensors. So that's pretty easy. It's connected to one of the front ones. It goes over here and that's it. It measures the pressure. Now on the other side, this sensor over here is measuring the oxygen concentration. The rest of it is just interfaces and battery and so on. If you look underneath it, you can see that the oxygen enters one end of this long tube and it comes out of the other end. In this situation, the other end tube is just left freely, so the oxygen comes back into this and then exhausts through the chassis. There's a hole in it. So how does this actually work? Well, if you look on one side of it, we see that there's a 2-pin device on one side of this tube, and if you look in the other side of it, there's another 2-pin device on the other end. They look very, very similar, and down the middle there's 2 other connectors there that goes something in the middle of that tube. Now if you think a little bit about it carefully, if I can separate these, it should become pretty obvious what this is doing. This is an ultrasonic oxygen sensor. Now unlike the electrochemical one, this has no consumable parts, so in theory it should last a very long time until these ultrasonic sensors eventually give up. The nice thing about using an ultrasonic sensor is that you can measure the speed in which it takes, the time it takes for the ultrasonic sensor to go from here to here, and that's going to be a function of the density of the material that's in the middle. Now it turns out that oxygen's density is 1.429 grams per liter, and nitrogen's density is 1.251 gram per liter. So oxygen is quite a bit more dense. Now of course, the flow can also be measured, because by measuring a Doppler shift between the two ultrasonic sensors, you can also measure the flow. If you know the temperature of the gas, and that's exactly what this little sensor down the middle is, it's just an NTC thermometer in the middle. So you measure the temperature, you look at the Doppler effect, you look at the delays, and then from that, you can estimate the density of the gas. And from that, you can estimate the relative concentration of oxygen with respect to the other gases. It's not going to be super accurate, I think plus or minus 5% or so, maybe plus or minus 3% with some good calibration, but it will work just fine in this situation. So yeah, another very clever sensor design. Okay, so the system's been running for a few minutes and I've allowed it to stabilize. I'm passing the output of it through this flow meter here, which also allows me to adjust the flow if I want to. Right now it's wide open. The unit is set to 1 liter per minute. Here on the left side is the oxygen concentration. It's missing a decimal point. That's because this is a very simple LCD screen. And on the right side, we have the flow in liters per minute. This number and this number on average agree, so that's pretty good. This means that this is not even remotely close to 90%. So just like I thought, that number in the front is of course completely fake. But I wonder that if I limit the flow a little bit, because I don't need this much flow for the experiment we want to do, I wonder if we can get the oxygen concentration to be better. So I'm going to artificially limit it from the outside because the unit is already at its minimum. Let's see if that makes a difference. So I have managed to reduce the flow to just below 0.5 liters per minute. You can see we are reading 0.4 liters per minute, and we are now at 83.2. So we gained 6 or 7% or so. Not that much actually. So even at less than half of its rated flow, it still does not meet that 90%, which is disappointing. The zeolite containers inside were quite small, so that's not that surprising that you can get the flow you're looking for, but it's well below what it should be. That's what happens when you buy the cheapest oxygen concentrator you can find. Now, before we try to liquefy oxygen, it's really important to understand some of these elements' properties. For example, if you look at its phase diagram, it immediately becomes obvious why it is so difficult to get a hold of liquid oxygen in the first place and why it is difficult to store it. Looking here at the x-axis, we have the temperature in Kelvin. And you can see the highest temperature on this plot is 200 Kelvin. That's minus 73 Celsius. So this is already pretty cold. At this temperature, you basically have dry ice. You have solid CO2. Now on the vertical axis, we have pressure in kilopascal. Atmospheric pressure, 1 bar is 100 kilopascal. So we're sitting around here. Now, one way to get liquid oxygen is simply to chill it. If you cool it enough to be around 75 Kelvin or so, you can liquefy it through condensation. And then oxygen can exist in liquid form at atmospheric pressure if it is really, really cold. Unfortunately, you cannot liquefy oxygen by pressurizing it to a point where it is liquid while it is at room temperature. It's just simply not possible. At extremely high pressure, other things can happen too. Oxygen, there is solid oxygen and some really unusual material properties at extremely high pressures. But that's the reason why you cannot buy a canister of, for example, liquid oxygen at room temperature, like you can with propane, for example, which is liquid inside the container at room temperature. So therefore, pressurization is out of the question, and it's going to be very dangerous anyway. So it is much better to find a way to cool it down, to liquefy it. And we're going to explore several techniques to do that. Another thing to keep in mind is that if you make liquid oxygen and then put it into a canister and seal it, it will begin to evaporate, and eventually the gaseous state will continue to rise in pressure as it rises in temperature. It is extremely dangerous because it will not remain in its liquid form. So having this now, with this knowledge, we can go ahead and figure out how we can liquefy it. We can also contrast the behavior of oxygen to something like carbon dioxide, which can exist in liquid form at room temperature if the pressure is high enough. Here at the bottom, the temperature is now in Celsius. So let's say 20 degrees Celsius. If I go all the way up here, yep, if I have very high pressure, 50, 60 bars or so, I am able to liquefy carbon dioxide and have it at room temperature. So it's a lot easier to transport as a result. Of course, if you take it in here and immediately lower the pressure, it's going to go from liquid directly to solid because the pressure is going to drop, the temperature is going to drop with it, and that's why dry ice is around minus 80 Celsius. You can see that it can exist at atmospheric pressure if it is really cold. These are really interesting things. Phase diagrams are of course available for pretty much everything, and you can look at things like triple point where the 3 phases exist at the same time, and some of these experiments are actually within the reach of household items, and maybe we'll do those in the future too. So here are two pressurized containers. On the left we have oxygen, on the right we have propane. And if you look over here, there's 400 grams of propane in this, and there's only 40 grams of oxygen in this one. And that's of course because the oxygen tank on the left has no liquid oxygen in it because it is sitting at room temperature. In fact, they have to pre-charge those to 400 to 500 psi. And in hospital settings or in some industrial settings, oxygen tanks can be 2000 psi. Whereas this propane container in here is in liquid form at a fraction of the pressure. And that's one of the reasons, again, why it is so difficult to transport oxygen. So we've concluded that in order for us to liquefy oxygen, we're going to use cryogenic techniques. Now we can use liquid nitrogen to do this because the boiling point of liquid nitrogen is lower than the boiling point of liquid oxygen. And a lot of people actually do produce liquid oxygen this way. But that would mean that we would need to constantly replenish our liquid nitrogen, and it defeats the original problem we want to solve, which we want to use only electricity to accomplish this. Now check out this fantastic piece of engineering. This is a superconducting filter, and it has two distinct components. It has a cryogenic Stirling engine, and it has inside of this vacuum chamber an actual superconducting filter, which becomes superconducting at 77 Kelvin, which means that this Stirling cryocooler can actually reach that temperature. And they are thermally coupled together. Now this is going to be the subject of a completely different video where we take this apart, take a look at exactly how those filters are built, how they become superconducting, what their architecture is, and actually measure them. So I'm going to put that aside for the time being. We're going to focus only on this engine. So how does this engine even work? Now, the operation of this Stirling cryo engine is wonderfully fascinating, a marvel of thermodynamics in itself. Essentially, we're using electricity to do the work for us, and the electricity is moving thermal energy from one point into another, which is not very uncommon. All refrigerants basically do this. Even a Peltier cooler is using electricity to do the work, although that's a solid-state device, a completely different principle. Now it all starts when we apply an AC current in a sinusoid form into an electromagnet. That electromagnet itself is sitting in the presence of a very strong magnetic field with some permanent magnets. That means that it's going to cause an oscillation. It's going to cause that piston, like a solenoid, going back and forth, and you can adjust the speed in which it goes back and forth by adjusting the frequency of the AC signal applied. Most of these operate around 60 Hertz or so, which is still pretty quick for an oscillating piston like this. And hopefully by now it is obvious what the job of this piston is going to take advantage of the ideal gas law, compressing and expanding the gas within the chamber of the engine in order to create that temperature difference we're looking for. When the piston is moving forward, it's going to compress the gas over here. At that moment, its pressure will go up, its volume comes down, and its temperature will go up. At that moment, the rejection area of the engine will try and take as much of the thermal energy away from the gas and dissipate it into the environment. If you can keep that gas and bring it down to room temperature, now you have a high pressure gas that is not hot anymore. And then you can push that forward to the front of the engine, the cooler tip. In this cold tip, we're going to expand the gas to the opposite. And at that moment, any thermal energy from the outside will be sucked in, and then the cold, of course, tip will become colder as a result of that. And you can repeat this process back and forth, compressing and expanding. Now, there are a lot of subtleties in here besides that. For example, this material down in the middle, this is a regenerator. Because it is impossible to completely remove the thermal energy from one side and completely cool down the other end from the other side, it is not possible to reach a lowest level of possible temperature differential by just doing this technique alone. So what they do is that they put a very porous material with an extremely high surface area. The advantage is when the gas flows through it, it is able to completely remove all the thermal energy from it. But it's even more subtle than that, because you want this to remove a lot of the energy locally, but you don't want it to be passed back and forth very fast. So this material is porous, has a lot of surface area, but doesn't have a very good thermal conductivity in this direction. So there is a huge temperature difference in the front of the regenerator compared to the back of the regenerator. Essentially, it is kind of like a delay. And as a result of that, you're able to very efficiently exchange heat between the front and the back of the engine at the same time and slowly climb down the temperature as you move along this curve. Without the regenerator, you can cool it, but only at a limit. Now, the gas that's typically inside of this at very high pressure is helium. They use helium for several reasons. One is, of course, because it's a noble gas, it's inert, it doesn't interact with anything. But also, helium has a very high thermal conductivity compared to some of the other gases. It's, for example, an order of magnitude more conductive than, say, nitrogen is. So helium will help in this situation to be able to remove the heat from it as much as possible. So the cycle is going to continue, and this tip is going to get colder and colder and colder. And in an architecture like this, you can easily reach to below -200 Celsius, which is incredible in such a small volume. Now, there are several things to keep in mind. There's, of course, a certain lift capability of this, meaning that there's only so much thermal energy that you can dump into the cold tip while maintaining its temperature. That's the lift capacity of the engine. At the same time, it's really important to keep the rejection temperature at room temperature and not let it get hot, because the temperature delta between these 2 points has a certain limit. If I end up heating up this area, this cold tip will simply not be able to reach its lowest possible temperature, and the entire efficiency of the system will be heavily affected. So we have to be very careful on how we manage the thermal profile of this, and I'll show you what we can do about that. The other issue is that this piston moving back and forth 60 times a second, there's a lot of mass associated with this, and you have to absorb that in some other way. Otherwise, this thing is just going to vibrate like crazy and rip itself apart. So what they do is that they put a weight on the other side of it, and they balance it perfectly so that they oscillate in opposite direction, and then the entire system stays at equilibrium. You can tune the springs over here, just like any mechanical system. It's like an LC oscillator. You tune them and you match them together, and then they oscillate at exactly the same frequency, and the whole system becomes stable, and the vibrations are heavily minimized. You can even make these absorbers at the end active that dynamically adjust themselves, which is helpful in situations where the frequency is changing, for example. There's a lot of other things like air bearings in here, which allow these things to slide without creating a lot of friction. You really don't want friction in here, because friction causes heat, not to mention wearing out this, which is going to mess everything else up. So yeah, this is the principal operation. It really is a beautiful thing. Even though the fundamental concept is simple, the engineering in here, the valves, the regenerator material, and exactly how you tune everything, the dimensions, there's a lot of work, of course, involved in this. But I'm really excited to try it out. So now we need to worry about how to run this Stirling engine on its own and worry about this thermal profile. When you put the lid on top of this, there's another piece of metal that comes over here and sits on top of this area, which is the heat rejection area of the Stirling engine, which means that when this fan is running at high RPM, all the air that is pulling through are going to go through these fine fins, and that's how this is going to be air-cooled. So we need to do something similar and move a lot of air through this rejection area to maintain its temperature near room temperature. Now there's also a few other things. You have to be very careful running these Stirling engines, because how much power you put into them is going to be depending on the temperature of the cold tip. Otherwise, you're going to slam that back and forth and actually internally damage this. There's control loops within this that automatically do that, which means there are several temperatures and parameters of this that are controlled by the circuit board, which is on the other side, which I will show you. The most critical part is to measure the cold tip temperature. Now that temperature sensor is inside of this vacuum chamber, so we have to emulate that characteristic somehow, and we'll do some reverse engineering to accomplish this. There's also a resistor here which measures the rejection temperature, which is easy because that's sitting outside. That's also connected to that board. So one thing at a time. First, design a thermal profile around this. And here is our cryo setup for liquefying oxygen. There's a lot going on here, so let me go through it. In the middle is our cryo Stirling engine. At the very top, this is the balancing counterweight, and the cold tip is at the very bottom. There's a heat sink attached to it. I'll show you that in a second. That's also where the cryo temperature sensor is. This body in the middle is where the heat exchanger is. This is a 3D printed piece, which my brother helped design. And what it does is that there's a fan on this side and a fan on this side. And this is going to suck air in through all those fins and blow it out from these sides. These two fans create a lot of negative pressure inside of this chamber, which is sealed around the engine, allowing it to pull as much air as possible through those fins. I'll give you a view from this direction in a second. And there's a fan here at the top that blows across the body of the cryo engine itself, and that's going to cool the electromagnet and everything else, trying to lower the temperature of this as much as possible. Now, in order for these fans to not run at 100% all the time, there's also a temperature loop that I have created, which I will show you, so it runs them at a reasonable speed. Essentially only runs them as fast as it needs to. Now, there is a lot more temperature things to consider, because we still want to liquefy oxygen, so we have to have a chamber here at the bottom to maintain that temperature, and there's another 3D printed piece here, which is going to act as a lid, is also going to guide the oxygen into the chamber. And here's the view from the top showing how I've attached a Stirling engine to the aluminum frame. There are 3 pieces of metal plates over here. Each of them are sitting on top of a rubber vibration absorption joint here. And that's going to further reduce the vibration from the engine itself. And here's the counterweight. You can see it. This one is tuned at 60.3 hertz. And the fan on the other side that's blowing onto the body. So this structure is just simply to make sure that the entire frame doesn't vibrate as much as possible, because the interface at the bottom would also need to be as stable as it can be. And here's a fan controller. This fan controller has a sensor on the rejection port of this, and it's going to adjust the fan. Nothing unusual. You can buy these fairly easily. And there's a fan in the front, and of course the fan in the back into the chamber. And here's a look from the bottom, so you can see how this 3D printed piece over here hugs the rejection heatsink so well. So all the air will have to be forced to go through these fins before it reaches this cavity and then blown out using the fans. Now this piece down here is also 3D printed, and it has to have some important properties. First of all, it should be mostly hollow, because you really want to have as much of a thermal isolation as possible, and there is some polyethylene tape at the bottom of it to further increase the insulation. Basically a lot of porous airs in it. And it gets mounted and tightened fairly tightly onto the actual front of this. Now this is the cold tip. It only gets cold in this area, and this is a heatsink copper attached to it using some screws. And you can see a wire coming through out, and this wire is a diode attached to this heatsink, which is going to act like a cryo temperature sensor. I'll talk about that separately. And it goes into this, and internally within this there are pipes dedicated to route various things. One is to get this cable out. There's also a pipe over here which brings air or oxygen in this case in, and then it releases it into the chamber over here. And there is another one over here which can exhaust it out. So we can build some pressure in this, and we will see that too. There are 2 temperature sensors on the rejector. One is over here, which is controlling the fans, and one over here, which is going to the control circuitry. So these 2 wires, this is going to measure the cryo temperature, this is going to measure the rejection, and both of these are required by the control software to actually operate this entire thing. And then there is the power from the engine itself. That's this one over here that has to go through there, and of course all the fans need electricity too, and they're also coming from that board. So it's a nice compact setup. These 2 temperature sensors are quite different from each other. This is a thermistor, an NTC thermistor. This one is actually a PN junction, and the unit inside the vacuum chamber of the superconducting filter is a tiny surface mount wire bonded component. Now we can't really use that because it's really fragile, so I had to find a replacement diode. I'll talk about why that PN junction actually works. Now this over here, this heatsink, the purpose of it is to increase the surface area. So basically oxygen will condense on this once it's cold enough, and it's going to drip down as liquid. And this needs to come down to about 75, 77 Kelvin or so, and that way we'll have a continuous flow of oxygen being created. Now remember that any heat that escapes this entire system is lost, so you really have to insulate this as much as possible. Now I've done that to the best I can using the insulation above here, so whatever touches this hopefully should be fairly well insulated. Of course, cooling the rejection is really important, as we talked about, but we still need to kind of put something down here to enclose this so we can collect our liquid oxygen. Now the vessel that we use to collect the liquid oxygen is pretty important, because we need to maintain really cold temperature inside of it. So I tried some of these completely transparent dewars, which are double insulated. And if you put over here like this, you can seal it, and actually it does come down to temperature, and you should be able to see liquid oxygen dripping. It's nice because you can visually see what's going on. But this is not well insulated at all. It starts to frost on the outside, and the heat getting into it, it just simply cannot maintain a sufficient temperature to keep that liquid oxygen and building it up. So then I ended up with something like this. These are just simple double insulated stainless steel cups that people use to drink hot or cold liquids. And I put some polyethylene tape around it. Now we can go like this, and we can basically hold it in place by putting something underneath it. And this works remarkably well. Even at completely minus 200 degrees Celsius, this thing, you cannot even tell that it is colder than the ambient. So it's pretty impressive that it has as much insulation. Then there's also a good seal from here to the top bottom of this layer over here, which means we can have some positive pressure built into this. And positive pressure helps a lot. You also don't want to have any flow. So you don't want the gas to be constantly pumping in here and escaping from the other side, because the gas coming in is warm. So you only should really replenish it when you need to. So you do need to build some positive pressure in there and maintain that pressure and not allow the gas to flow too much, so you can maintain the temperature. So we can do that and have some mechanisms to actually measure how well that is working. Now it turns out that silicon PN junctions are actually reasonably well behaved, even down to below 50 Kelvin. Here on the left side is a plot of the forward bias voltage of a p-n junction silicon diode across temperature at a fixed excitation current. And look how nice and linear this curve actually is. Even down to about 50, around 25 Kelvin, some nonlinear effects take over, and of course the p-n junction behavior completely changes because everything is just so cold. But on the right side is a derivative of the same plot. And look, for the majority of that temperature range, you can maintain that 2 millivolt per degree Kelvin, which is very characteristic of a silicon p-n junction. So if you calibrate this, you can get extremely accurate reading. You can see it begins to change a little bit down here, but we really want to be able to bring it all the way down to here in order to be able to make the measurement we want. So what we really want is to pick any silicon diode, as long as it's reasonably well hermetically sealed, that matches the forward bias voltage at the excitation current of our instrument, and then we can fool it and let it read that measurement instead, and it's going to be accurate enough for our purposes. Now you can see the excitation current here is kept pretty low. These plots are from a product DT670, which is from Lakeshore Cryogenics. I mean, these guys are masters at making cryo temperature measurements and building these kind of systems. And the excitation current is kept very low because you don't want to dump a lot of power into the diode, because of course it's going to change its temperature. I don't know what the excitation current of our instrument is, but we can measure it. It's pretty straightforward. And then we can identify a diode and fool the system into thinking that it has the diode that used to be inside its own chamber. And then we can close the loop with it. Yeah, it's pretty nice to see that this is possible. And here what it looks like when you look into the little heatsink connected to the end of the cold tip. You can see down the middle I have attached with some thermal glue a silicon glass package diode with the two wires going out and then going into the control board. The actual heatsink is connected to the cold tip with 4 screws. You can see them, they're all spring loaded. You really don't want to screw things in completely because of the huge temperature change, and things may actually break. So this way, yeah, there's some room and some movement allowed in here. But yeah, looks pretty good. And here's the main board that controls the entire system. And it's not just for running the Stirling cryo engine. It also has the power supplies and the control circuitry for running the low noise amplifiers, the superconducting filter, temperature sensors, and many other things. We don't need to worry about those components. We just want to make sure it works and can measure and control the Stirling engine. On the left side here, underneath this, there are several transistors that drive the actual motor itself. And here there is a little transformer, which I believe is used to monitor the actual phase and voltage of the current going into the engine, so you can constantly correct for that. So there is a closed loop to control that system, which is pretty neat. And a whole bunch of other op amps and other control circuitry. There is a microprocessor in here. And interestingly enough, in this portion of the circuit, it looks like this is capable of measuring 3 of those silicon p-n junction diodes at the same time, but only needs one of them to work. And that's probably because there are multiple versions of this product, some of them with fewer LNAs than the other ones. That's probably the reason. So I went ahead and measured the excitation current of the p-n junction, and it's 100 microamp. So now you can do some interesting things. I have put a potentiometer in series with it. Because the current coming into the potentiometer is constant, I can create a delta V across this potentiometer, which is going to remain constant because it's not changing temperature. That means that I can adjust the temperature that the circuit board thinks the tip is at. And I can make it a little bit higher or lower if I want to, depending on the junction of the diode you're choosing. And there's a distinct advantage to that. And I will show you once we're actually running it. That's really all we need. We can just control everything else from the computer because it has an RS-232 port. You can see I have the rest of the cables connected over here. Just a simple USB to RS-232 allows us to fully control that. And there's a software that luckily is available online. Some people have already downloaded and kept it, so we can use it to fully control this. It's a really nice and compact system. And finally, here's our overall setup. Our oxygen concentrator is going to produce oxygen at about 85% purity based on our measurement. Now, even though this is fairly dry, I'm still going to pass it through some silica gels to dry it even more, make sure there's absolutely no moisture entering our chamber. And then, of course, it goes into the cryo engine cooler. The flow of oxygen goes through the regulator here, so we can limit its flow, and then it's going to enter this chamber. Here I'm using the glass one just so we can see it initially, and the output of that comes out of the other side so we can measure the pressure, so we can find out what's the static pressure inside of the chamber. And here's the control board fully connected with all of the different temperature sensors, power supplies, and everything. And the remaining of the path over here coming out of the chamber goes into a Fluke 719. And here we can measure very accurately the static pressure inside of our container. So now we're about to run it. Before we run the engine, I made some minor modifications. I added another fan here from my OnlyFans account. That way we really can keep this cool. And I added a piece of cardboard here to maintain the flow across the top of the engine to to keep all the actual engine parts cold. And then here at the bottom, I switched out the glass container. It would just frost on the outside and you couldn't see anything on the inside anyway, and there was too much heat getting in. So this should be pretty good. So I have turned on the oxygen, but I have not turned on the cryo engine itself. You can see that we're maintaining about 1.3 psi inside the chamber. It's not fully insulated, so of course there's going to be some escape of gas, but maintaining 1.3 psi is pretty good. I have reduced the flow just as little as I can to maintain this pressure. So I think we have minimum leakage out of this and minimum heat getting back into the chamber. Now we should be able to turn on the engine. So Dr. Pooch, are you ready for the experiment? Good cat. And here's the control software running, and it's really neat. It gives you so much information. It really was built basically by engineers. You can see that it was built in 2002, and this engine has 68,410 hours of runtime on it, showing how resilient these Stirling engines actually are, how well they've built them for their application. So this thing has been up on the tower for 5 years or so. Now coming down over here, we can see that the cold temperature range reading is 303 Kelvin. So I have purposely adjusted that potentiometer I showed you to read 10 degree Kelvin above ambient. And that's because I wanted to make sure that the internal PID controller of this software, when it's trying to adjust the Stirling engine, doesn't get into some oscillation. Because the thermal profile and leakage of the actual vacuum chamber that this was designed for is very different than my setup over here. And I don't want to find all the PID coefficients. It's just easier to force it to be 10 degree higher so you can never really reach that temperature while still being close enough that it maintains self-operating of the engine itself. It also gives you power into the Stirling motor, the phase and everything, the error. But of course all of that is zero right now because I have purposely pushed it into shutdown mode. You can also adjust some of the set points like the oscillation frequency. I have set it here to 6.72 in my setup. And I have asked it to reach 75 Kelvin. Now, if it could reach 75 Kelvin, it will actually be 65 Kelvin because again, I have that delta of 10 degree built into it. There's also another temperature sensor, which is the narrow temperature sensor. It only kicks in around 83 Kelvin. It's going to do a different calculation, and that is, of course, maxed out right now. So we are reading the wrong thing here. Ambient around 21, and the cooler temperature about 16.7. It thinks it's a little bit cooler than it actually is. But other than that, it's pretty self-explanatory. I can put this thing into initialization and then starts to cool down, and then we should be able to see this temperature go down. And here's the counterweight in action. Look at this. Look at it go up and down. So these fans are starting because of course the temperature of the rejection is going to go up slowly and it's going to get pretty loud in here. And check it out, in only about 6 minutes or so, we are already sitting below minus 100 Celsius. So CO2 would be long solid at this temperature already. The rejection temperature 24.7 is pretty good. You probably can hear the fans right now. They're going at full speed in order to try and maintain this temperature around this value. And we're dumping just under 100 watts into the cooler. So this can go all the way up to 125, 130 is where I've set the limit. Some people push it even harder, but I don't think we need to do that for our purposes. Now, even though it only took 6 minutes to reach this temperature, it's going to take a lot longer to go from 171 Kelvin to 70 Kelvin. Now remember, you have to subtract 10 degrees from this because of the offset. So we're already pretty cold in there. And now after 35 minutes or so, you can see that we are within the range of the narrow temperature measurement. Now keep in mind again that you have to subtract about 10 from this, so it's really cold in there. We're dumping 126 watts into the engine, which is the maximum, roughly the maximum I have entered there. Yeah, it's going to continue working. Let's let it run for a little bit longer and see how much liquid oxygen we can get. So the system's been running for about an hour and a half, and I'm about to remove the container here attached to our system, and I thought we'll take a thermal image of it to see how well insulated it is. And really only at the very top, at the interface from the container to that top pink plate that you saw that I had 3D printed, was there anything lower than ambient. It's a 6.8 degrees Celsius. Is not too bad. Remember, inside of this container, we're at 77 Kelvin. So there's a huge difference in delta in temperature, and the fact that this is only cooling down to about 6.87 degrees Celsius is pretty good, I would say. And of course, as soon as you remove the container, it will instantly frost, which is the importance of having that air to be super dry so that it's prevented while it's inside of that container. And look at that. That's pretty cool looking, I would say. I should be able to just brush it off. Wow, that's still really, really cold. And here's the moment of truth. Let's pour this thing into a container. And look at that. Absolutely incredible. It's blue. just like it should be. This is of course now liquid oxygen. Now we have a little bit of time to do a couple of quick experiments with it. Now one thing is that if this is liquid oxygen, it should be paramagnetic, and that has to do with the outer free electrons of the atom itself creating a magnetic dipole. Here we go. Let's see. Look at that. That is the coolest thing. Here we go. That is absolutely incredible. It's a really beautiful blue color. So let's try it out with something that can actually burn. Okay, see? Instantly. Wow. Violent reaction. We can take a small piece of it. This is actually a pretty good glass tour because it's maintaining this very well. Wow, violent. Here we go. Wow, absolutely incredible. So of course it's needed to say that this can be quite dangerous because it is such a heavy oxidizer. But the fact that it is attracted to a magnet is still really an amazing phenomenon. And this really proves that it is indeed liquid oxygen. And the color also verifies that. The color is actually always blue, but the reason it's so obvious in the liquid form is because it's a three-body system, and liquid is much more dense, allowing it to interact with the wavelengths of light that are longer and filtering them out, and therefore being left with the shorter wavelengths, which are blue. Whew, got it out. Absolutely incredible. And there's still a little bit of liquid oxygen left at the bottom of this, and you can see this is a really good doer, and it insulates it very well as it's not boiling at all anymore. And that's not surprising, we saw the thermal image. So how much power does this thing consume? How much energy did we spend to create this liquid oxygen? Well, the oxygen concentrator itself is burning 121 watts. So we ran this for what, an hour and a half, so we can calculate how many kilowatt hours that is. At the same time, the cryogenic engine is burning about 189 watts continuously. Even though the motor itself is around 130, there is all the fans and all the electronics and inefficiencies of the drivers. So about 310 watts of instantaneous power for an hour and a half. And that's still a lot of energy that we dumped into this to get a little bit of liquid oxygen. But of course, that's not the reason here. The reason is to learn about the science, which is fascinating. And one more fire experiment. This thing never gets old. Amazing. And there you have it. I hope you enjoyed this episode and going down the rabbit hole of putting all these experiments and devices together. I really enjoyed working on this one. And as always, thanks to the Patreon and PayPal supporters. It takes very little to support the channel, but a video like this is a tremendous amount of effort and many thousands of dollars of expense of getting all this equipment and having them work together. And thanks to my brother for the 3D printed support, Ilya, my friend from XDev, and Ben from Applied Science for the consultation to get the cryo engine and everything working. As always, let me know what you think in the comment section, and I'll see you next time.